everybody. Welcome to Talks with Toe. I'm your host, Chris Toe. This podcast is brought to you by a couple broke grad students, science, I guess, and the First Amendment, because free speech. I'm joined today by a very special guest, Ryan Donahue.
Hey everyone, how are you?
Yeah, so Ryan and I have known each other for about, 2 years now?
2 years, yeah.
2 years now, here in grad school, and we're just going to talk a little bit about what you're doing in research.
Okay.
Also, kind of your background, how you ended up here in California, because you are originally from the East Coast, right?
Yep. Originally from New Jersey, born and raised.
Yeah, so I guess what kind of got you into biomedical engineering specifically as a field?
Well, biomedical engineering, I really started my biomedical engineering career at the high school level. I got into this high school called Biotechnology High School back in Jersey, in Freehold, New Jersey, actually. And they taught a lot of, it was more on the agricultural biotechnology side and, science-heavy school. It was a VOTEC school, one of 5 in Monmouth County, New Jersey.
Okay, and so what does VOTEC stand for?
Vocational technology. So it's, I'm not exactly sure what vocational technology is, but there were 5 high schools back in New Jersey and Monmouth County that they're technically public high schools. They're publicly funded through tax dollars, and being a resident of Monmouth County, you can try to get into one of these 5 schools. You can go to info sessions, check each out. They had one communications based. They had an allied health and sciences one, which my sister actually went to. They had a high-tech one, which was more like mechanical and aerospace engineering, which my brother went to, actually. They also had Marine Academy and Science and Technology, so like marine science and things
so that's
like
interesting.
that.
That means you and your siblings all went to different high schools.
Yeah. So me and my siblings all went to different high schools growing up, and we would always go back to our home high school, like Wall High School, where I grew up, Wall Township, New Jersey, for sports and things like that. That was kind of part of the agreement with the county-wide school district that you always go back to your home high school for sports. So, getting back to your original question, it was that school which really kind of started my interest in biomedical engineering, and I think something like 80% of my high school class went on to apply to be biomedical engineers, like majors.
Really?
For college, I think. Yeah, it was some high proportion. We had another handful of arts and another handful of social sciences and things like that. So
that's definitely interesting. I don't think anything like that exists in California, not that I know of. But
I haven't seen anything like it. Commonly what I've seen in like other parts of the country is some high schools will have like specific academies for like engineering or like arts or something like that. So that's kind of like the equivalent of what we would do back at these home high schools. Because the other unique thing is, we'd focus heavy on the biosciences or biosci, but we would also be, take English, history, social studies, all the typical high school classes as well at these schools. Okay. So we took Spanish as well, any typical high school classes.
Yeah, it's really interesting. I think that's definitely not super traditional in the sense of most schools. But I guess when you were in high school and you were kind of thinking about college, like what ultimately led you to UC Irvine specifically, and also just looking at colleges, like what was kind of your criteria for where you wanted to go?
So I'm a big beach volleyball guy, which is another part of me that very well, but I'll share everyone. I grew up playing volleyball in high school, and my parents met playing volleyball, so I really wanted to go somewhere where it would be warm and where I could play beach volleyball. So for my undergrad, I ended up at the University of Miami, which South Beach is right there. There was a good volleyball crew there. Didn't end up playing as much as I wanted to, but I was always determined through my college experience, my undergrad experience, to make it out to California. And, I applied to heavy on the California side. And, as an aside, Orange County and Southern California, and even some of Northern California in general, has a very heavy biomedical and, biomedical device scope to it. Right.
Yeah.
So
there's a lot of industry around.
Yeah, there's a lot of industry specifically in Orange County for medical devices, and then you get more into the biotech industry as you go more south towards San Diego. But yeah, I was really determined to make it out here to California, partially for volleyball, partially because I love the vibe out here.
So I'm guessing that it wasn't sunny during winter in New Jersey.
No, it's not at all. Yeah, it's
We're going to go on the record and say that it's not sunny in New Jersey in the winter.
Not at all. Don't get me wrong, I love New Jersey, but the winters were sometimes really gray and depressing during the winter, but I wouldn't trade my high school experience for anything. But yeah, I ended up at the University of Miami, wanted to continue into the biomedical engineering PhD program. I applied to, likes of UCSD and the joint program up between Berkeley and San Francisco. Was offered a couple masters here and there, and then, I was admitted to Miami, which was my undergrad institution once again, and then Rutgers, which is right next to home, 45 minutes from home. Didn't particularly want to go back to New Jersey. Don't get me wrong, they have a great program, and the faculty that I interviewed with were great. But I got an interview opportunity out here for UCI, and I wasn't admitted at the time for the PhD program. But I came out here and really showed that I wanted to be here at this program, and ended up getting admitted. And I was like, this is an no-brainer for me after I visited, and I wanted to be in Southern California. It seemed like the perfect pick.
Nice.
So,
yeah. That's cool. So I guess now, give us kind of a brief overview of what your research is now, what you're working with, kind of in layman terms, just because, we are used to talking to each other in scientific terms, and sometimes I realize that when we're with other people, we'll just talking about our research, and then you look around in the room and everyone's like, what the heck are people talking about?
Yeah, more recently I've been talking with my girlfriend Holly, about some of the stuff I do, and, she's like, huh? But anyways, so I really do regenerative medicine, which is the idea of, creating a part of the body or a part of a tissue outside the body and aiming to transplant it back for therapeutic purposes. So we're specifically in the realm of cartilage, so anything that is ends the long bones in your body, or things like the meniscus, which is a fibrocartilage. We aim to create this stuff outside the body, in vitro is what we call it, and place it into the body in vivo. So a lot of the work that I'm doing is something called the temporomandibular or jaw joint. There's a fibrocartilaginous disc, which is a specific type of cartilage that we are aiming to repair holes in, or something called perforation. So right now what I'm doing a lot of is creating an implant that we test outside the body and want to place into different animal models, specifically eucontaminated pigs.
And the end goal for this is humans, right?
Yes, the end goal for everything a biomedical engineering person does, I feel like, is for humans at the end of the day. There's a lot of basic science and things like that is sometimes more technologically advanced, and might be some sort of technology that can be used to advance a therapeutic. But at the end of the day, we're all aiming towards, helping better human life.
So the jaw joint, obviously, it's something that people use every day to eat and stuff like that. How big of an issue is the joint deterioration? And specifically, I'm assuming this joint is the one that connects your jaw to your skull, right? Am I right, Glenn?
Yeah, you're right. So there's actually two jaw joints, one on each side of your body. So if you split your face down the center, there's one on your left and one on your right. So it's a bilateral joint is what we call it. The prevalence of what we call TMDs, or temporomandibular disorders, or disorders of the jaw, whatever you want to call it, there's epidemiological studies that say as high as 25% of the general population can have some sort of symptom of the joint. Yeah. Now, whether those symptoms are painful and manifest in a bad, painful way is another story. So, we say as much as 25% of the general population can have a symptom of TMD, but whether that deteriorates to the point of getting a hole in your disc, or getting some sort of osteoarthritis, which is just breakdown of the cartilage and underlying subchondral bone beneath your cartilage in the joint, it's a much smaller proportion.
So are people who have, I guess, family arthritis more prone to getting this type of deterioration in their jaws?
I'm not entirely sure about that. You know, there's a lot of different forms of arthritis. There's rheumatoid arthritis, which is an autoimmune disease. There's osteoarthritis, which is just general breakdown of the cartilage and subchondral bone. So, you know, it really depends on, you know, which type of arthritis we're talking here, I guess.
So, really quick, what does subchondral mean?
Subchondral, sorry. The bone beneath the cartilage. Okay. Sorry. Like Chris said, we can get very wrapped up in the terms that we use sometimes, and so if there's any term that you hear me use, just feel free to ask.
So it's the bone that's directly like touching the cartilage. Would that be an accurate description of it?
Yes, exactly. So the cartilage that we're aiming at is actually not touching bone. Okay. The anatomy it's a interpositional disc between cartilage and bone. Okay. The interpositional disc, and then cartilage and bone again. Okay. So, you know, there's cartilage and bone on the base of your skull that touches the disc, and then there's, from the other side, from your mandible that comes up to your jaw, there's also something called the condyle, and then cartilage on top of the condyle. So there's actually 3 different cartilages within that joint, but we focus on the disc because that's what is commonly perforated during temporomandibular disorders. So
interesting. So how are these disorders, I guess, usually diagnosed? Is it just people go into the doctors and they like complain about joint pain, or?
Yeah, a lot of people will start to hear clicking, and then it'll slowly degenerate into painful symptoms. You know, whether it's pain when they're opening or closing their jaw, like during chewing or talking. Mm-hmm. Commonly enough, oddly enough, it's commonly treated by dentists first. Mm-hmm. It's commonly, you know, seen as like, you know, mispositioning of the teeth, so you have an overbite or an underbite or a crossbite or something like that, and dentists see that as, you know, that's why you're getting pain in your disc, so they'll commonly try to treat it through different dental appliances first, so mouth guards, splints, etc., etc. There is a specific subset of surgeons out there called oral maxillofacial surgeons, which are sometimes from the traditional MD route and sometimes from the DDS or dental specialty route, that will actually go into the joint and do surgery, open surgery in the joint. You know, there's a number of steps before that. Mm-hmm. You know, you can go and do something called arthrocentesis, which is just an arthroscopic or joint, which is pretty much them just putting different small holes in your joint and rinsing it out with saline, trying to break up the issue there.
So like that rinsing with saline, which is like, I guess basically like salt water. Like, what is the goal of that? Like, how does that help the joint?
They'll try to get rid of any debris in there or anything that they just try to open it up more and make it. Commonly, what will happen is there's something called it's essentially the joint fusing. So the disc will fuse to either the top or the bottom, so they'll try to break it up through that. They just try to clean everything up with arthrocentesis, and the outcomes for patients show less pain. So, you know, that's why things are commonly done. You know, anything to help relieve.
That quality of life. There are a lot of things I'm realizing that, you know, we do these treatments mostly to improve quality of life too, because it's like the best we've got, but not always going to solve the issue. Which is like, I guess why we exist.
A lot of treatments, especially in the TMJ or the jaw realm, will be for palliative, not reparative purposes. So they're just addressing the symptomatology of everything. So it'll be painkillers, steroid injections. You know, they even do physical therapy of this joint to, you know, as first steps, non-invasive or minimally invasive steps before they go to, you know, opening the jaw up and doing surgery. Really, only 5% of patients with TMDs are even candidates for open jaw surgery. So that's kind of like a very small proportion, and that's really kind of what some of my research is going towards, trying to create like this mid-stage intervention, you know, before it's so broken down that you have to get a total joint replacement, which is pretty much a plastic and metal appliance that they put in your joint as a replacement for it. But still, after like this arthrocentesis or arthroscopy treatment that we look at like in earlier stage generations.
Interesting. So I know you've been going up to Davis a lot, UC Davis. Tell me what that experience has been like, and also kind of why you've been going up there so much.
Yeah, so UC Davis, I'm collaborating with a doctor named Boaz Arzi. He's a veterinarian, oral and maxillofacial surgeon. Great guy, and we've been collaborating to actually put some of the cartilage that I've been making down here at UC Irvine into Yucatan mini pigs up at Davis. So I've gone up there now 4 times since this time last year. I have another 9 or 10 trips scheduled until July of next year. And it's all going towards placing some of the cartilage that we make, and it's just a square patch, 8mm by 8mm patch that we put in to try to heal defects that we create in these Yucatan mini pigs.
Interesting. So you guys create these defects, or I guess holes in their cartilage, and is the goal of your study to give cells like a place to regrow, or are you actually putting cells back in to the cartilage?
So what we put in is self-assembled. So I won't get into the self-assembling process right now, but it's a living piece of cartilage. So there's actually cells in it, approximately 7 million. And we grow these cells over 2 to 3 months to get them to create a piece of cartilage. And we aim with placing a biologically relevant piece of tissue into the hole to get it to heal. How that healing happens, whether it's the native host tissue cells that grow over the defect, or whether our implant is just providing some sort of regenerative capacity for the native cells to grow in, or whether those cells that we put in, those donor cells that we put in, come out and create the tissue, we don't know. At the end of the day, it would be great to know, and we're going to try to do some studies in the upcoming manuscript that we're preparing for all these animal studies to see whether we can see if the host cells are migrating in, or vice versa, if the donor cells are migrating out into the host tissue, to see what the mechanism is. But at the end of the day, we're getting great healing, and that's what matters.
It's always interesting in biology because we're kind of like faced with this, like, I feel like this everlasting problem of like, you have cells that you can't see physically without a microscope, and then you want to see how they act, but once you put them into a living organism, it kind of removes the ability to use a microscope in a lot of ways. It's like, how do you do that? So
and we've played with, I've looked up a ton of ideas and played with a ton of ideas about how can we track these cells, and that's a whole nother aspect of biomedical engineering that we could get into. If you talk to our friend Austin, he's doing a lot of microscopy work and how we look at cells on a subcellular level and how they're functioning, and using analytical tools like that. We've played with the idea of transfecting cells, which is, for those listening, just putting in a foreign piece of DNA to make the cells produce an green fluorescent protein, that will allow us to identify the cells on a microscope slide after we take the tissue back out. We've played with that kind of idea, different radiological or radiographical labeling technologies and things like that. So
interesting. So are the cartilages you guys making human cells, or are they like actually pork cells?
So they're porcine cells. So part of the approach that, the reason we use porcine cells is because if you put human cells into a pig, you're going to have a greater immunological reaction. You're going to have, it's called a xenogenic approach, right? What we're going for is an allogenic approach. So one pig cells, taking them, we actually take the cells from the rib, chondrocytes rather, and put them into the pig jaw of another pig. So it's an so that's the idea that we're playing with. Eventually, when we do this in humans, we will want to take human tissue and put it in humans. We've done benchtop studies where we can do the same approach that we do with the pig cells and human cells, showing that there's an analogous approach there. So
nice. Yeah, that's super cool. I mean, I think obviously there's a lot of different parts of the body that you work on and stuff, but I feel like the joints are not always talked about as much.
Right.
Like everyone kind of knows what arthritis is, but it's not like a super prevalent thing because I feel like most people don't go to the doctor immediately for it too, right? They kind of like just deal with the pain for a while.
Right. And, there are a lot more diseases out there that are, worse or, affect a higher percent of the population or things like that.
Yeah.
There's not many that can degrade the quality of life, such as osteoarthritis or temporomandibular disorders. TMDs are actually the second most common musculoskeletal disease, I guess you could say, in America right now, according to the NIH, I believe. So, there's a $4 billion market around, TMDs in general, and there's huge untapped potential. There's a lot of different groups pushing for better treatment of TMDs right now. The TMJ Association is one of those. It's a patient advocacy group of about 1 million right now.
Oh wow, yeah, that's a lot of people.
Yeah, and you look at like cardiac disease and things like that, and there's probably a greater proportion, and there's a ton of research going into cardiac disease and things like that. Right now, even at UCI, we have a whole cardiovascular center, Edwards Life Sciences Cardiovascular Center, right? That there's research going into, and we don't just do the jaw, we also do the knee, we also do some of the spine, we also do some of the nose.
Yeah, it just happened that your specific project is...
Right, yeah.
So other grad students in your lab are kind of working on these other areas.
Right, yeah. Everyone in our lab kind of has like one specific, I guess, area that they're working on in terms of everything. Ben, our other friend, is working on articular cartilage of the knee, for example. So.
Okay, nice. So I kind of found that like when you talk to like people who kind of aren't in the academic world and you tell them that you're a biomedical engineer, you get a lot of questions like, oh, like what do you do with that? Or like, does that mean you like are like building like organisms or something? Like people kind of have this, I feel like, this understanding of biomedical engineering that for some reason doesn't seem super accurate, but like, what is your response usually when people ask you that question? Or like, why are you doing a PhD in biomedical engineering?
I try to avoid... I say I'm a grad student most of the time, but I try to avoid, like, I'm doing a PhD in biomedical engineering when I meet people for the first time or something like that. Do the same. Yeah, just because it's, like, easier not to explain. But I guess my best response for that would be, we're trying to better human life by finding new solutions for unmet needs within the biomedical field. So that could be something as simple as designing a better tongue depressor, for example. Technically a tongue depressor is a biomedical device. Yeah. Or it could be as complicated as something as designing the next MRI or CT scanning machine or something like that.
Which is also biomedical engineering.
Yes, that's very biomedical engineering. What you do a lot more computational biology work, and you look at...
Yeah, I mostly do genomic data science, that type of stuff,
Right, yeah, biomedical engineering can even get into that, bioinformatics. It's such a huge and broad field. But at the end of the day, anything you see in a doctor's office was probably created by a biomedical engineer. And, while a lot of those things have been created and that's done with, there's always the next generation of medical devices that are upcoming and still being created, things down to stents, pacemakers, insulin pumps, continuous glucose monitoring through the insulin pumps, things like that. Even some, now with social media and the smartphones, you can have some things personalized on your phone, like personalized medicine apps.
Yeah, personalized medicine is like kind of the buzzword of biomedical engineering, I feel like, right now.
Yeah.
Like the amount of articles that I've read just talking about personalized medicine is like kind of absurd because people also leave it very generic. But I don't know. What are your thoughts about that? Because like I feel like that's a very huge topic in academia right now.
Yeah, I mean, personalized medicine, for those of you that don't know, is a treatment for a specific person for a specific disease and the specific type of disease that person has. So I think one of the classical examples is cancer, right? So one cancer treatment, for example, radiation or chemotherapy might not be as effective for a bloodborne cancer as a tumor-based cancer or something like that. So the idea behind personalized medicine is targeting either genetically or however it might be a treatment for that specific patient. And I think it's a great idea. I think it's going to be with the advent of AI and as much computational power is being put into biomedical engineering now, I think that's going to help make great strides in personalized medicine and looking at past patients and how they responded to treatments based off their genetic basis, and you get a new patient who has a similar genetic basis. Does that same treatment work for them, or is it different? I think we're going to start to make huge strides and see a lot of computing power going into biomedical engineering in the very near future.
Yeah, actually, when I was doing some research into my thesis, when I was doing my qualification exam, there was a stat where there's one database that was just like a genetic database in the European Union.
Yeah.
And in 2008, that database had 50 gigabytes of data. By 2012, that was 120 terabytes. And that's 4 years, right?
Right.
And it was an exponential increase, so I don't even know what it is now.
Yeah.
But I can tell you that the data that we're working with is 3 terabytes on its own.
Right.
So I think personalized medicine is definitely slowly becoming a reality, but there are definitely a lot of infrastructure problems that I think the scientific community and also just general governments are gonna have to figure out. How do you store and manage data like that?
Right.
And how do you do it with patient privacy in mind? I think those are questions that are very much still open-ended.
Yeah, and
which is kind of interesting.
Yeah, I don't think going to patient privacy and HIPAA compliance and things like that. I think that might have to be almost rewritten. How everything's going to be handled in the future with, especially genetic data. Genetic data is going to be the key. To personalized medicine, I think, and how do you de-identify?
How do you de-identify data from someone's genome?
Right.
There are ways to do it, but then in doing that, do you kind of lose the power of that data?
Right.
Yeah, it's definitely an interesting topic because I think we're living in a world that most people didn't think was possible, 15 years ago.
Well, you think about, when computers first popped up, you didn't think the smartphone revolution was going to be the way it is now, right?
That's
they
really
just
true,
they just launched the iPhone 11 the other day.
I saw the commercial for that. Yeah. Although apparently the price is not going up for once.
Yeah, right. Yeah, I think the new iPhone 11 starts at $700, and
which is still incredibly expensive.
Yeah, right. Especially for a phone. I'd rather buy a new computer with as much computing power.
That's almost like a full month's rent in Irvine. That is a full month's rent in some places in Irvine. But if you guys are listening to this and you're not in California, yes, it's that expensive to live in California. So, I guess what kind of misconceptions do you see people having about scientists in general, when you're talking to normal people? Because I kind of get the sense that when I tell people that I'm doing these things in medicine, they immediately kind of assume I'm way too smart for them, but I'm just a normal person too, trying to figure out things. There's a lot of things I don't know about medicine stuff.
Yeah, I feel like this is as much of a stigma anymore, but when you say PhD or engineer, you're expecting somebody with tape glasses and a pen in their pocket, the stereotypical nerd or geek, I guess you could say, that was more of a thing of our childhood, I think. But I a lot of stigmas along the route of grad students or PhD students in the sciences, is they can't socialize, they can't be normal, they can't act normal in a social setting or something like that. But I think there definitely is a spectrum of grad students, and there's both ends of the spectrum. There's some people that are a bit more awkward, but there's also perfectly completely normal people that you would see walking around the streets of Irvine or whatever city, you know, like some very talented artists that I know are also pursuing PhDs, you know, whether it be musical or, you know, painting or whatever media, you know, like some of the YouTubers I know are doing PhDs, and, you know, there's a whole spectrum of people that, you know, are really pursuing higher education, and specifically with biomedical engineering. I think there's just a vast, you know, spectrum of people.
So like, now that you've been in like the thick of grad school, like you've kind of been doing this for, you know, a couple of years now, like what have you kind of learned about how grad school worked? What were some things that you didn't expect that you experienced while you were in grad school?
So when I first came into grad school, I had this very idolized view of the research I wanted to be doing, especially here at UCI. Like, I visited with a couple professors. Their research was really interesting to me. It was similar to what I was doing in undergrad. Previously in my undergrad, I was doing more like stem cell work and differentiation or differentiation. So creating, you know, taking stem cell and putting it through this culture, you know, growing it into another type of terminally differentiated cell. Taking like something that's more immature and making it mature. I was specifically interested in doing that in ophthalmology. So I got here and I wanted to do like stem cell research in ophthalmology, and I found like a professor that would maybe take me on as a PhD student, and didn't end up panning out, and you know, I ended up where I'm at now, and it's a great scenario. And one of the biggest like pieces of advice to those coming into grad school is be open to new types of research, and this is one of those exact reasons why you have to come in and be willing to make a change and figure out new interests, and you know, go with the flow a bit. You know, whether the go with the flow is because of funding reasons,
which is a whole nother conversation.
Yeah, that's a whole nother conversation. You know, some PhD programs will fund you for the first year and do rotations like UCI does. Other smaller programs or more, I guess, well-developed programs will actually admit you to a specific faculty advisor in mind, and you have to accept, you know, that offer with that faculty member.
Right. It's really not consistent across universities.
It's not at all. Yeah, I know. You know, University of Miami, my undergrad would admit me to do research with my undergraduate advisor, which would have been great. You know, I would love to stay, but you know, when I got the opportunity to come out to California, explore a bit, you know, I really wanted to do stem cell research at the Stem Cell Institute one way or another. Turns out, you know, the opportunities weren't there as the way I wanted them after being in grad school. I knew I didn't want to be in academia after grad school. I wanted to go into industry. And
that's still the case? Do you?
I'm playing with the idea of academia a bit more now. Not as much as it would take to convince me, I think. But basically, I didn't want to have to TA every quarter for all of my grad school career. So
That's me.
I mean, for some people it's great. Yeah. Like, it provides funding, and you know, it provides valuable experience if people want to go and be a professor at university. Like, the TA positions, they're great. I just didn't want to be pulled away from my research because I wanted to finish in 4 years if possible, and you know, be in and out and get into the workforce as soon as possible. So you know, I guess my biggest piece of advice to those in grad school or going into grad school would be, you know, be willing to explore and open up your options, and you know, prioritize. You know, if you want to be in academia, prioritize TAing and, you know, getting teaching experience. You know, and if you don't, then maybe try to go where the funding is, and you know, figure out if the research is something you would be willing to do for 4 years. Just because you have your research during your PhD doesn't mean you're tied to it after, though. Unless you know. But you know, the biggest thing I've been told, or the best thing I've been told, is PhD teaches you how to learn. And I think a faculty member at Rutgers told me that when I visited. And that's so true. You know, like, I rotated in 2 different labs. I learned about that one lab that I started in for 10 weeks, and I became not an expert, but very proficient in that area. And, we're getting a bit into that area now in my current lab. We're getting a bit into the immunology side, and I just have that background now. But I'm also bolstering it with things I'm learning now. I learned about a whole nother field now. And it's not like you can't do it again in a postdoc. It's not like you can't do it again for a position, job in industry.
Yeah, that's true.
So
I think it's very interesting, even for me, when you do your research, you end up going down these really weird rabbit holes where you just have to learn something else that you never thought you would have to be, because it's technically in another field.
Right.
But I feel like when you're in a discipline like engineering, you really can't avoid doing a lot of cross-disciplinary research, because you just have to.
Yeah. I mean, biomedical engineering, going back to the breadth of it, right? The spectrum that we were talking about earlier, it could be anything from computational robotics, tissue engineering, more basic science, biology, chemistry, material science. You have to learn so much. I'm learning everything from, the immunological system, macrophages, how they polarize, down to, elastic materials and biphasic materials.
So what are macrophages?
Sorry, so macrophages are a type of cell in the body. There are, I guess, the first cell to respond to a foreign invader or something bad in your body. And we're interested in these because they drive the overall immune response towards chronic or acute. So you can either have an initial wave of inflammation and it can subside and go towards a healing state, which is more acute inflammation, or you could have it just stay in that initial inflammatory state, which is more chronic.
Right, and then chronic is always an issue because then you have more of that pain.
Yeah. The more inflammation, the more pain, more deterioration, loss of quality of life. So we're doing some of that research there. And then, we also do mechanical testing, so testing how strong the tissue that we create is, and, based off those numbers, saying yes or no to implantation. And, we model the materials, soft tissues in our body in a couple different ways, using viscoelastic properties and things like that.
Okay, and viscoelastic properties are specifically I guess, how elastic, but not exactly. Right? So how would you explain it? That one's kind of a hard one.
Yeah, so when you think of elastic, you can think of a rubber ball that you bounce on the floor, right?
Right. Yeah.
Or when you bounce it, or a rubber band. A rubber band is a better analogy. You pull it to some far length and then it snaps back to its original length. So that's an elastic response. A viscous response, that's a bit harder.
It's more like a fluid response, but it's a slow moving.
Yeah, it's kind of like a jelly or a syrup of sorts, flowing. And, it's really that combination of different responses that makes a cartilage function as it does. So, yeah, we don't need to get too much into that.
You kind of need both, obviously. Yeah. That's how your joints are able to, do this and be okay.
Right. Yeah. There's also so that's the loading function of everything. So you step and you put the equivalent of a weight of an elephant on each of your knees every time you step.
Really?
Yeah. And I think you do 10,000 cycles per day or something like that. Maybe not that many.
How does that work? Is it just because it's pressure over area?
Yeah, it's pressure over area and the equivalent forces that develop in the knee over the equivalent area.
That's pretty crazy.
Yeah, it is. There's always a slide on my advisor's talks that he puts an elephant on a knee skeleton, and I always forget to take a picture each time because I want to commit those numbers to memory.
Yeah.
But
that's crazy because that's just, I don't know why, but this is maybe I used to do long jump.
Mm-hmm.
And that's pretty tough on your knees.
Yeah.
I can't even imagine what kind of force that must have been. Well, long jumpers must be putting their bodies through,
right?
Or athletes in general,
right? Yeah. I mean, in the jaw, the forces that develop are on probably half a magnitude or less than the knee, but you wouldn't think that, the same forces that develop in your knee are the same that develop in your jaw, and you think, your knee and your jaw are probably two of the most commonly used joints in your body, probably the jaw a little bit more. It's because you chew and speak so much across the course of a day,
right.
Unless you're, a runner or something like that. But yeah, in addition to the force, there's also the lubrication properties. So, you think of, when you step, you put a force down, and, you want your cartilage to be able to withstand that force, but you also want to be able to smoothly move your joints. And, lubrication properties are another crucial characteristic of cartilage as well that is thought of, but not as much as forces in my world from a day to day. So
yeah, I kind of want to go back to talking about like grad school in general, and like I guess for people who are like thinking about going into grad school, or like maybe like have worked a bit, like are now thinking about going back into grad school, like do you have any like advice about how to apply, like what you should be looking for when you're applying? Because there's definitely a lot of things that I know I wish I knew before I got into grad school, but
I would say look not more on school level, but more on advisor level. So your advisor is essentially your boss, who's going to be your boss for 4 to 6, 7 years, some cases, in PhD programs. You want to be able to have a good relationship with your boss and enjoy the research you're doing. I said a little bit ago that you might need to take a compromise on your, research that you might be doing. That's because if you have a good advisor and you aren't, as enthused about the research initially, at least, I think, people can sometimes make that compromise and get enthusiastic about the research. That's kind of what I did. When I first initially came in, I thought musculoskeletal tissue engineering was kind of like the old stuff, like from, the
back in the day.
90s and early 2000s. But, because it's some of the older stuff, it's some of the stuff that's first reaching the clinic now. And that's what's making it more exciting to be, for me personally,
because you kind of have the feedback of a clinical setting of like knowing how patients actually need these treatments. Yeah,
that and the field of musculoskeletal tissue engineering is just that more developed. So going back to your original point, a question rather, be willing to make a compromise on the advisor, and I would shop around more on the advisor level than school level. That's kind of, I shopped around on the school level when I was initially applying, but
that's true. It's not like undergrad where like the name of the school makes your PhD. It's actually really like the school name almost kind of doesn't matter.
Yeah, it I would say it helps, but it's really the name of your advisor, because at the end of the day, you might end up getting a job. If you get a job as a postdoctoral fellow, which is the next logical step for most PhD students, it's going to be most likely a colleague of your advisor or some connection that your advisor has. It's the same way in industry a lot of the time. Like, you network and make all these connections. Your one boss might tip you off to another application or something like that. The next logical step in your career path, and it's all about the network once you end. Definitely shop around more on advisor level, not as much of a school level. Make sure you have funding if possible. If possible, do not go do a PhD program. I would say do not go do a PhD program unless you have full funding. In the sciences, most of the time, the school will provide that to you one way or another, whether you have to TA 1 quarter, and then you're as a graduate student researcher or a research assistant. Make sure you're not paying anything out of pocket. While you're gonna have to do work and it's gonna be long hours in grad school no matter what, make sure you're not doing those long hours and paying out of pocket for it.
Right.
In my opinion, sometimes what'll happen is you'll apply to a PhD program, and I got a couple of master's offers instead of PhD programs, and they'll say, "Oh, you can transition to a PhD." If you really want to go to grad school, I would suggest definitely applying PhD and seeing what kind of offers you get. if all the schools you apply to say, we don't think your resume is strong enough yet, come do a master's with us, you're going to pay out of pocket for a master's for a year or two and then get admitted to the PhD. But if you can do a PhD right off the bat, it's much better.
Yeah.
Financially savvy to do it that way, I would say. So
I would definitely agree with that.
Because you came in and you transitioned from the master's to the PhD, right?
Yeah. I mean, it's been stressful. I've been able to swing it.
Right.
But it's kind of just another thing that you have to think about.
Right.
That kind of distracts you from your research. It's definitely possible.
Right.
Don't get me wrong, but you have to be a lot more proactive about making sure you have the funding. I would also say it's totally okay to take more time and take a break if you need to.
Right. Yeah.
Because most PhD programs, if you get accepted in the PhD program, even from the master's, they kind of want you to finish the PhD because it looks worse for them if they have people who do a PhD part way and don't really finish,
Right, yeah, and dip out with the master's or something like that.
Yeah.
I would just say be financially cognizant of the program. Make sure you do your research into, what you're getting and what you're not getting, whether you're getting health insurance, that's sometimes a big factor for some people. What kind of pay you're getting for the area you're living in. Our first year was more than enough, but it quickly dropped our second year in the PhD program here at UCI just because of some, year-long fellowships, and then, you get dropped to the pay grade of a GSR, which is fine. We still make do with everything that we have, and, I'm grateful for, what we do make and, our rent on campus and things like that, but just be cognizant of your financial situation, and especially if you're coming back and you're a bit more later stage in life, you have kids or a significant other, you're married or anything like that,
Yeah, you gotta make that decision.
Yeah. So
that's great. Well, I guess the last thing I wanted to talk about was academic papers. It's a very interesting process, I guess you would say. I think a lot of people aren't very much aware of how scientific papers are written, why they're important, and you're published now, 2 publications at least, right? Maybe 3.
Yeah, I have 2 publications. They're both reviews, possibly a book chapter, and I'm working on a 3rd publication.
So what is that process like? Obviously, there's writing involved, so people who are averse to writing know that as a scientist you still have to write a lot.
Yes.
But yeah, what is that process like? How do you get your paper published?
Yeah, so the way it worked for me, I was lucky, I guess. Both of my first reviews were invited reviews. So if your advisor is a well-known person, I guess, they'll sometimes be invited to certain journals. In this case, it was the Journal of Biomechanical Engineering for me, and Transmolecular Medicine, a cell biology trends journal, a cell trends journal. And you'll get a specific invite to write a paper. Sometimes if you're submitting blindly, you'll have your paper, the idea of your paper, and it's not out there already, so you'll send a solicitation to the journals that you want to be in, and they'll give you general feedback and say, yes, we want to see your draft of this paper. So from there you kind of start writing. You put it in the format that they want. A lot of journals have a very specific format.
Very specific.
Yeah, especially when it comes to more primary research articles, like experimental articles, that is, not reviews necessarily. They have very specific sections, so they want to see, your abstract have 5, subsections: intro, methods and materials and methods, results, discussion, and conclusion. Others will be a bit more loosey-goosey, I guess, and, let you write how you want to. And reviews can be a bit more flexible in that respect. You can create your own sections and highlight what you want to highlight. From there, you'll submit your paper to the journal. It'll be peer reviewed. meaning, 3 other scientists from the field will, 3 to 6, 7 even.
Right.
Minimum 2 usually, will review your paper. And then, you'll get comments back about things they want to see changed. Things like spelling corrections, grammatical corrections in some case if you didn't write your paper very well. They'll have
proofread your paper.
Yeah, proofread your paper. You'll have, anything like that, and then sometimes the editor will also give you comments back about, what they want to see.
It should be interesting to note that these editors usually are PhDs themselves. Right?
Yes. So all these people typically have some sort of doctoral degree in the field. Whether if you're submitting to a more clinical journal, some people even have MDs and PhDs. In our field at least.
They're the crazy people.
Yeah, MD, PhDs. That's a lot of education, folks. But writing can take anywhere from 2 to 3 months to a year. It really depends, how many authors you have, what kind of paper you're trying to write. The newest paper I'm trying to write has an author list of 10, spread from anywhere from Massachusetts down to Texas, up to UC Davis. So that's going to be a tough one to write, but.
So get this. That just reminded me. when I was doing my research, I was working with this database called the Cancer Genome Atlas.
Yeah.
Right? So it's like a nationwide NIH-funded, National Health Institute-funded database. There's this one paper in Cell. It had 45 authors because they basically just put every person who had any involvement in any of the process of this pipeline to make this database as an author.
Yeah.
And I was like, that's
absurd.
Ridiculous. Like, literally half the first page was just people's names.
Wow, jeez. So I can't imagine being part of a 45 author list for just one.
That's probably the most ridiculous paper I've seen. Yeah. I mean, it was like a very important paper, but it's just it was just ridiculous that they put everyone's name down.
Yes, it really depends on the philosophy of the corresponding author. Some people will say, as little of a contribution as running a data set or something like that, you're deserved to be put on paper, like pipetting a 96 well plate of cells or something like that, or doing one assay. Some others will be like, no, you have to help write it and have a more intellectual contribution on the which makes sense. Yeah, that's more the route that my lab and my advisor goes. You have to have some sort of intellectual contribution to it, and that's why our author lists tend to be on the smaller side. 10 is actually quite a bit for us.
Yeah, I actually think most of our department kind of writes papers that way.
Yeah, I would say. I've seen some papers with 15, 20 people on it, but I mean, everyone's different in that respect. But where were we? We were saying that.
Yeah, so the process could take up to a year.
Oh yeah, it can take even longer. For some of these bigger journals, I've heard going back and forth 3 or 4 times until you get a paper just the way the editor wants it and just the way you didn't want it. But at the end of the day, you make compromises with the editor so that you get your paper accepted. There's this fine line of saying, yes, we acknowledge that this is important, but we don't want to put it in our paper, kind of thing.
You kind of need to maintain the integrity of your research.
Right. It's not even an integrity thing. It's just sometimes reviewers and editors will suggest something so far outside the scope, or something
unreasonable to accomplish in a reasonable amount of time.
But after you'll commonly get a set of reviews back. You'll make edits. You'll write a cover letter to the editor and the reviewers and say, we made these changes. Our lab does it in a fashion. We do line by line. On line 377 of the manuscript, we made this change to reflect this comment, or this comment that was made by reviewer number 2. And we say in a fashion that we thank the reviewer for their comment and respond back to them, kind of thing. So for my Transfecting Molecular Medicine paper, we did that once and submitted our edits, and 2 or 3 hours after we submitted our edits for the first review, it was accepted for publication.
Oh, wow. Yeah, that's pretty fast.
Yeah. Then commonly from that, you'll have to make some more minor changes and things like that. Spelling, grammatical things. They'll proof it, which means they'll put it into the format of the journal. You'll get to see all the figures you made and all the text you wrote and the pretty journal.
Nice and pretty,
nice and pretty. You'll get to make comments on that, make sure they did everything correct, and then anywhere from a couple weeks to 6 months later, it'll be officially published. So.
So how important is that to like a scientific career?
So for academia, it's paramount that you have a number of good publications and quality journals, and that you actually have publications. For industry, it's a good resume booster, I would say. It's nothing bad. Like at the end of the day, when you're a grad student or a postdoc or a professor, you're measured kind of against your publications. That's kind of like the measure for success in academia, your publications, both quality and quantity. If you have if you have 300 papers that are published in like no-name open access journals or something like that, they say they're peer reviewed, but maybe not so much as up to the par of like the Elsevier journals or anything like that. It's not going to carry nearly as much weight as a dozen Cell Nature reviews papers. So quality is definitely up there in terms of importance. So
nice. Well, I think we've talked a lot. Thanks for your time.
No problem. Thank you.
You got any plugs? This is Ryan Donahue. Where can they find your work?
You can search me on PubMed, Ryan P. Donahue, if you want. You can find some of my more recent work. I'm not the urologist. I'm the guy with all the cartilage papers.
Some other common name, but
I don't know. Follow me on Instagram, rpdonahue7 if you want.
Follow me on Instagram. There you go.
So,
Thanks for your time.
Right. Thanks, Chris.
Thanks for tuning into this podcast. Make sure to like and subscribe. Talks with Toe is written and produced by Chris Toe. To learn more about Ryan Donahue's work, you can find him online at the Delta I website, or search for the Athanasiou Lab at UCI Biomedical Engineering. His publications are titled Remaining Hurdles for Tissue Engineering the Temporomandibular Joint Disc in the journal Trends in Molecular Medicine, and Considerations for Translation of Tissue Engineered Fiber Cartilage from Bench to Bedside, published in the Journal of Biomechanical Engineering. Music is by Purple Planet. You can visit their website at purple-planet.com.